Okay, good morning once again. So, in the last session, we have gone through processor architecture as what exactly we can say with the internals of the architecture because architecture and organization we have already seen the core difference within the first module, right? And we have thoroughly covered it what exactly is architecture, what is organization. And in the last session, we have gone through in depth as what are the various architectures supported and utilized by the manufacturers and its importance, say it be in terms of CISC, that is complex instruction set computers, and we have gone through RISC, that is reduced instruction set computers, right? So, we have gone through the historical perspective as it all started with accumulator and index registers, along with beginning, it was only single accumulator that was present. Later on, several other innovations were there, but primarily it was CISC that is continuing till today. And after this, there was a risk that is a reduced instruction set computer somehow nowadays picking up the case owing to the high power requirements, and so we have gone through the importance of instruction set architecture as why it is needed, because until and unless a common instruction set architecture is being defined or architecture is being defined, various organizations processor organizations will become difficult. Not only become difficult, running the softwares seamlessly will become a big issue whenever we will be having such kind, if it is not uniform, right? So just imagine that a software is being made after 5 to 6 years of efforts. And if you say that no, now this particular architecture is not available, so all things will be in vain. So preferably, uh, instruction set architecture is usually being kept consistent. Uh, there was 32-bit architecture earlier, and gradually we shifted to 64-bit. But the shift is quite smooth, and we have seen that particular era. Apparently, somewhat 3 to 4 years it took for this particular shift, and the best part was backward supporting was also there within 64-bit. Say it be if 32-bit softwares were supported, and because of that, the change was very seamless. Okay. So that was the case. But nowadays, when the whole industry has been shifted, so hardly you find any 32-bit softwares. So this 3 to 4, or you can say 4 to 5 years of shift that has taken place. But say it be, I think, somewhat uh, in 2010 to 2015, as far as Indian perspective is being considered. And later on, the 64-bit architecture is continuing, right? And even today, we are having several variations by the 64-bit architecture only. Okay. So we have gone through the basic definitions and analogy as what exactly we mean by instruction set architecture, what is the importance of instruction set architecture, who will be using instruction set architecture, means who will be the stakeholders or the people utilizing instruction set architecture. So we have gone through like assembly language programmer, the compiler writer, application programmer, or someone who is writing the hypervisor. Nowadays, hypervisor is totally depending on the architecture as well. So that way, it is acting as a bridge between, you can ultimately say that whatever be the hardware we are having and the software that will be written, correspondingly, it is acting as a bridge, right? And after that, we have gone through various components of instruction set architecture as the type of instructions, the addresses of instructions, categories, then the instruction sets, say it be stack architecture, accumulator, register architecture. So the whole history was seen, right? But it's not that particularly important. Later on, we have seen the importance of ISA, as said be if operating system writer is there, someone, some team writing the operating system. Okay, Google Android. So that has totally changed the mobile industry, right? Even when iPhone is very prevalent and iOS is very prevalent, popular, stable, so whatever you will say, but ultimately with the advent of Google Android, things has been changed, and now even in televisions and even in laptops, so you are having the OS. Laptops they are having the Chrome OS, but in television also they are having the Android OS, right? So other companies are having their own OS. Say it be LG is having Web OS, Samsung is again having some OS, right? So later on we have gone through RISC and CISC as what exactly is the difference between reduced instruction set computer and complex instruction set computer, right? So we have seen the structure. As if we see, then reduced instruction set computer, we will be having the hardwired control unit, data path, data cache, and instruction cache will be there. Ultimately, all will be connected through the main memory, right? And we have gone through CISC, and you can see the difference between RISC and CISC architecture. Okay, so this is not only in terms of instruction. So till now, what we have seen is in terms of instruction, uh, RISC and CISC are having few differences. Okay, but internally as well, main memory is somehow connected to instruction cache, and just see the differences, observe the differences. In future, in upcoming slides, you will be having a look at one more difference between the RISC architecture and CISC architecture, right? So you can see that main memory is only connected to the cache over here in case of CISC architecture, and REST instruction and data path control unit and microprogram control unit is there in terms of CISC, while in case of RISC, main memory is directly connected with the instruction cache as well as data cache. So altogether, the cache is divided it into two parts. One is instruction cache, and other one is data cache in terms of RISC, and ultimately getting the control signals from the hardwired control unit. So for the time being, just have this in your mind and try to see the differences. But in upcoming slides, you will be having some more differences, some crisp differences corresponding to RISC and CISC. Okay. Now, if we talk about features, so whatever we have discussed in the last session, so we can conclude with it. Ultimately, CISC obviously may take longer than a single clock cycle because the instruction is complex. So it's quite obvious that when we are executing the instruction through the clock ticks, of the processor. So ultimately, one clock cycle will not may not be sufficient enough because the instructions are complex, and that's why we will be needing longer clock cycle. And this is very obvious. The length of the code will definitely be short. Uh, just recall the example we have taken. Say it be multiply, right? So if I have to do 2 multiplied by 4, in case of CISC, it will be somewhat means internally they will be having the circuitry so that they can do multiply 2 comma 4 2 and 4. So the length of code will remain short, while here in case of RISC I may be utilizing the addition operation, and I have to go through that addition operation, or 2 plus 2 plus 2 plus 2. Then only I'll be able to get the final result. Okay. Then programming in assembly language, yeah, it's somewhat more accessible because again, the difference between C and Python. So now if we see someone that okay, write something in C where a lot of uh, libraries needs to be added, then the functions or the methods needs to be utilized, and finally somehow you will be getting some program, right? On the other side, Python, lot of libraries are there, and because of that, things are quite easy. Means if I have to edit something in PDF, if I have to, just a recent case was there that whenever examinations open book examination, BITS has instructed that watermark slides should be there, and they have come up with a solution that okay, this is how these are the standard watermark slides that you should make. So one of the faculty came out with a Python code where the watermark slides can be generated. We just have to give the reference of the original slides, and apparently the program and the program was merely of I have counted it 15 lines, right? So that program was taking the PPT as an input and apparently converting it into combined PDF with the watermark slides. So what I mean to say is the number of uh, the accessibility or the number of instructions will definitely be reduced whenever it comes to the CISC, right? So it will be focusing on creating instructions on hardware. Say it be multiply. So it will create multiply on the hardware, or hardware itself will be processing the multiply instruction. So that obviously it will be faster because we are getting it done through hardware rather than somehow tweaking it through the software, right? Advantages, I think now you have an idea, but I would like to listen from you as what do you think are still the advantages of CISC? Yes, anyone, I'm allowing mic to you. Just a minute. Yes, anyone, if you would like to specify that what exactly are the advantages of CISC? Yeah, okay, not an issue. So I'll just try to sum up as what exactly will be the advantages. Ultimately, if you see that CISC is right from the beginning as a stable architecture and lot of developments in terms of assembly code, in terms of what you can say, the legacy systems, those which were developed over CISC, right? So that still needs CISC as the architecture and is one of the main reason why still CISC is more prevalent, right? Not only that, but every to shift everything to RISC, things will be quite difficult. Somehow, Apple have started it by utilizing it into M1, M2, M3, and M4 chips, where now they are having the operating system based on this RISC architecture, and that's how means ultimately RISC is being supported. Okay, there was a case. You just go through it. It is very interesting, and I think in the next session we will probably discuss it. That mm, Zoom was very popular when in the COVID days, and later on when this M1 and even I don't know for M2 or not, but for M1 I am very sure that Zoom was not installed or we were not able to install Zoom on M1 chip, right? It's not only because of the support that or because of CISC and RISC, but there were several other technical reasons. So whenever you get some leisure time, just try to explore the historical perspective as why Zoom was not installing on M1 chip. At a later time, they have rectified it, and finally they have made the architectural changes, and then only Zoom was installing on M1. Right. I have taken some screenshots corresponding to the error message that we have received, but I'd like to, I want that you people should ultimately go through the case as a case study, and then we can have a thorough discussion on it. Right. So, as compared to the advantages, then ability to perform complex instruction is obviously one definite advantage with CISC. Then programs require fewer instructions to execute. That's quite obvious because most complicated instructions are being handled by the hardware itself. So as such, the instructions that we have to write are few in number. Hardware support is better, and if we talk about better suited for application that requires complex operation. Okay, so this is a typo. I'll correct this. It is CISC. Okay. Disadvantages we already have seen because if you imbibe the complexity within the hardware, the power consumptions will be huge. And if we talk in terms of the servers, again, this will be a big trouble, right? So increased complexity can lead to slower processing time. So this is one more case that if we put much of the complexity within the hardware itself, right? So just because of the circuitry, say it be, if only fewer instructions are there, then ultimately it will increase the speed. But when you keep on including the complex instructions, so that may lead to slower processing time, right? And obviously increasing cost, the power consumption. So this is a basic point-to-point comparison between RISC and CISC. So we have already seen this. This is something that we will be looking at. That it uses a hardwired control unit. So if you recall the von Neumann model, so we have seen that control unit is one of the major component of von Neumann model, and the control unit that is being used by RISC is hardwired, and the control unit used by CISC processors are microprogram control units. So this is the core difference because the instructions are reduced here. So RISC is okay with the hardwired control unit, while in case of complex instruction set computers, uh, because complexity will be huge. So rather than hardwired control unit for generating the control signals, CISC ultimately utilizes the microprogram control unit. Then transistors, yeah, that's quite obvious. Code size, this already we have seen. The use of pipeline are simple in RISC. Further, we will be looking into the concept of pipelining, right? So I hope many of you know the concept of pipeline, and those who are really working close towards architecture may have utilized it as well. In software, we use the pipelining very well. Okay, you can recall it from the CI/CD as well, where in CI/CD we utilize the concept of pipeline. But here, mainly, the idea of pipelining is to execute something in parallel so that if we can have the execution in parallel, ultimately, time will be saved, right? So, if say it be that we will see in detail, but for the time being, you just keep it in your mind that here in RISC, utilizing the concept of pipelining is somewhat easy. While in case of CISC, the use of pipeline is somewhat difficult because altogether instructions are complex. So how exactly the pipelining, because dependencies among the instructions will be there. So if output of one instruction is being fed to another instructions input, so ultimately they have to wait, and in such cases, pipeline will not be successful. And same is the case with SIS because it is having some complex architecture. So that's why uh, the concept of pipeline will be difficult to realize. Okay. Then instruction is executed in a single clock cycle, usually in a single clock cycle in case of RISC because the instructions are simple, fit in one word. That's obvious. The execution time is very short because instructions are small instruction or reduced instruction. So for a particular instruction, it is short. While in case of CISA, because the complex instructions are there, time will be more. So this how the program written for RISC obviously needs to take more space in memory because again you need to 2 plus 2 plus 2 plus 2. So this is for 2 multiplied by 4. While in case of CISC, ultimately it will be carried out by the processor only. So you don't have to utilize much of the memory in case of CISC. Okay. So this is the example that I'm quoting right from the beginning. So multiplying two numbers. So in case of CISC, it can be a multiply instruction where I may be writing that okay 2 multiplied by 3, or I may be writing 5 multiplied by 2, and that's how the circuitry will be supporting the multiplier instruction. So this we have already seen. While this will be the reduced instruction set computer approach, where the processors will be utilizing these steps. Say it be loading uh, means load the data into A, then load the data into B, then product into B. So I think this will be considered. I'll correct it. Right. So, excuse me. So these may be the steps that first of all we have to load the data into A, load the data into B. We have to do the product, and finally, whatever be the result, then we will be storing it. There is no need, I think, for this particular instruction. So I'll correct it and then we'll share. Because by default, whatever be the product, that will get stored in the instruction or the variable A. Okay. So ARM processor, this we have discussed in the last session because I was keen to communicate you as what exactly is the history of ARM processor. So ARM stands for Advanced Risk Machines. So you can see that it all started with Acorn computers. Then they named it as ARM, that is Advanced Risk Machines. And gradually it is being adopted by Apple, the RISC architecture, or you can say the ARM machines, right? So those who have not attended that particular session, just for their information, that this advanced risk machine or the ARM or the overall organization, they only give the architectural perspective. They are not the manufacturers, right? And all the mobile or you can say smart devices or portable device manufacturers nowadays using the RISC architecture and utilizing this architecture given by ARM, right? That is advanced risk machines. Okay, and the best example that we recently can quote is Apple M1, M2, M4 chips. We'll have a quick video about the ARM processor.
And have a fan in it. ARM's compute platforms are the most power efficient on the planet, and their performance is increasing more and more. ARM's performance per watt, or the performance per power used, is incredible. It's to the point now that 70% of the world's population uses products powered by ARM technology, and so of course, here at CES, it's hard to find something that doesn't have ARM's technology inside. They're in TVs, like this new LG transparent OLED TV that you can actually see through. And it also has a contrast screen to turn it back into a normal OLED that just comes up motorized from behind. It's pretty cool. Along with all of their OLED TVs, though, they're all powered by ARM. Even tablets like this ultra-portable Lenovo M11 benefits from the power efficiency of the ARM cores and the fact that they can run cool without a fan. They're in smartwatches like this Garmin Lily 2 that won a Best in Show award from CES this year, actually, that has up to 5 days of battery life, is powered by ARM CPUs, as are most of their other smartwatches as well. Chromebooks like the Asus Chromebook CM30 I saw at the MediaTek booth with MediaTek's Companio 520 chipset inside that's using ARM's CPUs and GPUs. It's also detachable, affordable, and it's military standard compliant against drops and shocks. There's gaming devices that you probably already know and love that are here, like the Sony PlayStation VR2 that's powered by MediaTek and ARM processors. Even Exeger Powerfoil solar cell technology is being used in conjunction with ARM technologies inside all sorts of devices, from Adidas headphones to Urbanista portable speakers and more. And even in cars here, there's ARM everywhere, being used for all sorts of components, like this, for example, Electro and Digital Cockpit. That's a curved screen display that uses ARM to power the dashboard that's new here this year.
Right, so you have seen variety of devices, right from the handheld devices, say it be the tablets or televisions, not only that, speakers, headphones, and even in the cockpit to its extreme,
I
they
have a fan
are
in it.
utilizing the ARM devices. Now we have seen the basic concept uh, gradually. Now we will see what exactly is the impact of risk and CISC in terms of cloud infrastructure. So CISC was utilized right from the beginning. So as such, there is no question that why or how exactly CISC is being utilized, because till now the cloud providers, they were using ultimately the CISC machines. But now the change is being there, where they have started shifting the deployment or the hardware to risk. Okay. And the point of consideration that we'll be making over here is performance and efficiency, energy consumption, uh, not only that, heat management, because the heat that is being generated out of the processor, because if you will be putting complex instructions, definitely the electronics will be needing more power and ultimately more heat will be generated. Then what exactly is the deployment flexibility and apparently the cost consideration uh, for having the cloud infrastructure. So we'll see one by one that what will happen. Performance and efficiency obviously means until and unless you are having some legacy applications to be running on the system or the cloud infrastructure, till that time you are good to go with the risk machines, right? So because if you see the performance in terms of per watt of usage or energy usage, ultimately risk will be proving to be a better solution whenever you will be doing it in this particular perspective, that is higher performance per watt. Because instructions are simple, so per watt, the performance that you will be getting in CISC will be high. Not only this, scalability will be a viable solution when it comes to risk. Just like I told you that within pipelining, you will be able to easily create the pipeline and do the task in parallel through the risk machines. While CISC will be preferable in terms of performance and efficiency, only in case you are willing to have some compatible applications with the older systems or legacy systems, those which are still developed considering the CISC architecture. Okay. The reverse example of Zoom is this, where in Zoom we were not able to install the Zoom on risk machine. Okay, that is merely an example, but you can have several such cases where something which is being developed while considering the CISC machines may not be easily installed, may not be smoothless, functioning in a smooth way with reference to CISC machines. If you put that software which is being developed considering the CISC machines, and if you put it on risk, so ultimately things will be different. Okay. And complex workloads. So whenever you are having some complex workloads, so that way again we will be preferring the CISC architecture. So I'm trying to find out other instructions as how exactly things can be done. So I'm in connect with a few of the manufacturers or the employees of the manufacturers rather, like Qualcomm and Snapdragon, the processor that is there. So trying to get some more detail out of it. Okay. So you can have this simple example. So Rosetta, which is a dynamic binary translator and is being developed by Apple. So this enables application built for Intel processors to run on Apple Silicon ARM-based Macs. So the Zoom that I was telling you, So that was not installing normally on the M1 chip. So ultimately, such tools needs to be used, and that's where I told you that normal case was not there, and it took a lot of efforts to install it on the M1 chip, right? So go through it whenever you will be getting some leisure time. Go through the case study. So this translator can be used whenever you are having some Intel processor or this CISC-based processor, but still you would like to run that application. But things are not that easy whenever such kind of translation takes place. Some things get translated, something may not be, so that may lead to some kind of error. There will be the performance issues as well, right? So whenever it comes to legacy applications, always CISC architecture will be preferable. In terms of energy consumption and heat, it's quite obvious that RISC will win the battle, where in terms of energy efficiency, because the instructions are reduced, definitely it will not be consuming much of the power. While in terms of CISC, where the instructions are complex, so power usage and cost implications will be high. Okay. Then deployment flexibility. So RISC already emerging architecture, and gradually we are shifting in the software side as well. We are shifting with microservices and containerization. Excuse me, which is again acting as a support for the ARM-based RISC machines. Okay, so you can just have an example. So ARM-based processors are gaining traction in the cloud market. This is one of the example, that is AWS Graviton instances. So AWS has started adapting the RISC architecture, and when you see the offerings of AWS, so they offer RISC machines through AWS Graviton instances, right? And obviously microservices and containerization, where that efficiently aligns with this architecture, because the core concept remains same with reference to the microservices and containerization, and as compared to the risk. While CISC, again, same thing will be there, that okay, whenever it comes to hybrid environment or some established ecosystem, because it's since long, and the ecosystem is established. So if you don't want any deviation, then go for the CISC machine, right? Cost, obviously lower total cost of ownership, TCO in case of risk. Definitely, there will be some initial investment in terms of cloud providers. So they need to do the initial investment, but ultimately, as far as the performance and power consumption is being considered, risk is on a leading side. Okay. So examples, AWS Graviton, we have already seen that they have started offering their EC2 instances uh, as a CISC machine. Okay. And Intel and AMD, you know very well, the 32-bit, the 64-bit architecture following the CISC machines, that is complex instruction set computers. When it comes to cloud provider choice, in terms of modern cloud providers, so they usually prefer RISC, because again, there are thousands and lakhs of processors running, and just imagine the cost that they can cut down using the RISC systems because of that, right? So even if you are, if 1 lakh processors are there, okay, and the overall electricity that you may be saving for a day is 10 units. So, or Yeah, obviously 10 units. So that way you can be saving 10 lakh units per day corresponding to a data center. So this is the difference that risk machine can bring. And that's why, as far as cloud providers are being considered, ultimately they have started shifting their architecture to risk. Right architecture, I think now you will be mm, judging it better as how exactly and when to use, right? So whenever some, until and unless some legacy applications built on CISC architecture is to be utilized, it's good to go with a risk architecture, having a lot of advantages altogether. The only thing is you should not stuck somewhere corresponding to the legacy applications. Okay. So these are all the factors on which the choice will be depending: performance requirement, then energy efficiency, software compatibility. That's why I was saying that the legacy factor also we need to consider. Okay. Now coming to addressing modes, whenever we need to locate the variables, if you recall the instructions, right? So we have seen architecture. Then we have seen instruction sets, right? So within instruction set architecture, we have seen instruction sets that, okay, arithmetic instructions are there, then say it be control instructions are there, and so on. Apparently, these instruction sets will be having the instructions. Okay, so suppose I am writing add B. Okay, so corresponding to these variables, we should be able to get the address as how exactly the value stored in B needs to be accessed. And if add is the instruction, and if only one variable is there, then how exactly the addition needs to be performed. So correspondingly, all these things will be controlled by the addressing modes. So whatever be the addressing modes, apparently you will be executing the instruction, fetching the values of the variables based on the addressing modes utilized by your architecture. Okay. So if you recall this slide that we have used very beginning, so initially it was the stack architecture whenever the instruction sets are being utilized. So even you can say addition, or you can say multiplication. So that was usually done by the stack architecture. Later on, accumulator architecture comes into place, where the example that I was giving, add A, add B. Why I'm saying this? Because accumulator I am trying to avoid A. So add B means whatever be the value is stored in accumulator, so that value will be added with B, and finally the result will be stored in accumulator. So this is the very basic example, and primarily accumulator was used to handle much of the operation, and later on general purpose, say it be the register memory communication comes into action. Okay, so why we are trying to deal with addressing modes and how that will help us out ultimately in the cloud infrastructure. Okay, so based on the, if I know the exact addressing modes that are being supported by the architecture, so apparently the programmer will be able to write efficient codes. Okay, so can anyone tell me that for whom the knowledge of these addressing modes will be favorable or will be utilized. Who will be utilizing the knowledge of these addressing modes? Yes, what will be the role within the programming
I
or
would say
software development? Yeah,
compiler.
yeah, very good, Ajit. So, whoever dealing with the low-level programming, say it be compiler, say it be hypervisor, okay, so many time it happens that when we execute the programs or the way programs or these systems, low-level programs are being written, highly impact the performance, right? So ultimately, all these will be utilizing the information of the addressing mode and whatever be the addressing mode supported. So picking out the best one for the required situation ultimately will be means we have to make a decision about the right addressing mode, right? So optimize memory access. So uh, you need to pick the addressing mode where we can have the optimized memory access, then efficient virtualization and multi-tenancy. Nowadays, processors are coming with support to virtualization, right? So not only that, you are achieving it through the software layer, but processor itself is providing you the concept of virtualization, right? So but still, if you would like to make it somewhat more efficient from the software side as well, ultimately you should be knowing the efficient this addressing modes, and that's what I was telling that the hypervisor writer or what Ajit has said, the compiler writer, ultimately they will be the one. Those who will be utilizing the information of the addressing modes and trying to give a efficient solution, right? So, a number of hypervisors are available in the market, but definitely the performance will be varying corresponding to different hypervisors. And addressing utilization of addressing mode is one of the reason why the hypervisors are having different performance. So that is one of the reason. I am not saying that this is the only reason, but definitely it will be one of the reasons between the difference in the performance of the hypervisors, right? Scalability and resource management. Obviously, to some level, addressing mode will be affecting the scalability and resource management of the cloud, security and isolation, somewhat which is coming direct or somewhat value which is coming indirect. So definitely it will be having different security measures, and apparently addressing mode can play a big role. Say it be if I'm storing address of address. Right. So first of all, I need to get that address. I need to reach to that address. From that address, I need to pick again the address stored at this particular address. And finally, I'll be getting the value. On the other hand, I may be having a direct case that, okay, address and at the address, I may be finding out the value. The other case can be I'm not using any memory location to store it. I am directly providing you the value. Say it be 10. If I'm directly providing the variable value 10 to be added into some another variable, right? So that way it will be yet another variation. So the security and isolation will be different in all of these three cases, and cost efficiency is again one more factor. So think over it. Today we'll be going through very basic concept, but think how in cloud, how in hypervisors, because ultimately virtualization is the underlying technology for cloud computing. Ultimately, for getting the concept of cloud realized, we will be needing the concept of virtualization, right? And how addressing mode is making the difference. Okay, so we'll quickly see the various types of addressing modes. Okay, so just have a look. Look, one is explicit addressing. Okay, so mm, you can say that whenever you are specifying the location of the data directly within the instruction itself, right? So that way you will be calling it as explicit addressing, where you are directly specifying the address or the location of the operand or the data to be fetched. So immediate addressing, absolute addressing, register addressing, base register, and index. So all these are the examples of explicit. We will see further. And implicit. Just see, feel the difference. Here we are providing the address in a direct mode. That's why we are calling it as explicit addressing. Here we or based on the instruction, it will be automatically known that where or which particular address to be referred. Okay. So just see the example, and I think you will realize the difference between the implicit addressing and explicit addressing. So implicit accumulator, if I am writing add B, so the other variable that I am picking is the accumulator. So that another value that we are picking is the example of implicit addressing. Because if we are using the accumulator architecture, ultimately add B is referring that B's value needs to be added into the accumulator, and finally the result again needs to be stored into the accumulator, right? So that way we can think over it. We can have stack operations, right? Because in a stack, we usually know everything needs to be done at the top of the stack. Means if I have to push it, then I have to do it at the top of a stack. If I have to pop it, then I have to do it from top of the stack. So those who are not from the CAC, so just for their reference. So this is a basic stack architecture where initially there is nothing, and whenever some values are being provided, it is being pushed one after the other. But the condition is whenever the value needs to be fetched, it will be fetched at the top of the stack. Right. So this value will be fetched, then this, just like your pleats within some function, right? So you will hardly be taking out this particular plate. Rather, you will be picking the top plate available. So again, what I mean to say is it is implicit that okay, only top of the stack is to be referred. Auto increment or decrement, that if I am writing say it be a plus plus, right? So that means one is to be added into the value whatever is available. So that way it is implicit because I don't have to refer to some another location apart from A, right? So A is already there, and plus plus will signify that okay, one is to be added. So that's why we are calling it as implicit, right? So these are few of the examples. Now coming to the explicit again. So we will see the various types of explicit addressing, right? So immediate addressing. Okay, so immediate in the sense that we will not store it somewhere. Directly we will be providing the value. the example I have given over here, we will be providing the value directly without storing it into some memory location. Okay, so you can just have a look. So add 10 to R1. So whatever be the value in register R1, we will be adding 10 to it, and that's why we say that it is immediate addressing mode. Okay. Uh, Direct addressing. So whatever be the memory address of the operand is specified directly within the instruction. Again, coming to the example I have quoted, this will be direct addressing where I know the address where the value is being stored. So that way we will be calling it as absolute or direct addressing mode, right? So uh, earlier, just feel the difference. Earlier I have written add R1 comma 10. That is 10 needs to be added to R1. But now supposedly we know that okay, the addressing mode is absolute or direct addressing mode that is being used. Okay, so just have a look. So this it will not consider as a variable or it will not consider as a value because the address mode that is being referred is direct addressing. So that's why it will go to this particular location that is 4000. So within the memory, it will refer to the location 4000 and apparently get the value which is there at this particular location. So whatever be the value of at location 4000, so that will be added to R1. Okay. So this will be the direct addressing mode. So operand address in the address part. So it will be there. So operand address 500. So I'll be picking up the value stored at the address 500. That is 800. Right. So the value is 800 and we can add it up to whatever be the addition operation is to be performed. Next is register addressing. Somewhat similar where rather than memory, we will be specifying the register where exactly the value will be there or within. To just have an example, so operand address will be the register's value. So operand value here you can see that okay, directly it is being stored into the register. So rather than memory, it is being stored into the register, right? So add R1 if we are doing this, ultimately the value is stored in the register R1 will be picked. Okay. So R1, the value stored in R1 is 400 and that value will be picked and will be utilized. The thing is, just see the difference. We started with add R1 comma 10. So this way we were giving example that this particular 10, preferably this is your immediate addressing. Add R1 comma 4000. That particular example we have seen, right? Now add, say it be if I am using accumulator or directly R1 comma say it be R2. So that way the values are available in the register and needs to be added. Okay. Excuse me. Next will be the register indirect. I hope by the name itself things will be clear to you as what exactly is register indirect. Okay. So primarily register indirect in the sense where address of the operand will be stored in the register. Directly the value will not be stored, the address of the operand will be stored. So first, by referring to the content available in register, I'll be picking up that content. That content will ultimately be a register. Okay. Sorry, will ultimately be an address of the operand. We will be referring to that address, and finally we'll be fetching the operand, right? So this way, now what will be the value that will be picked? If it is register indirect, and if R1 is the register. Yes, anyone?
700.
Yeah, so 700 is the right one because R1 is 400, and I just have to go to the 400 location and finally to fetch the value. Okay. Mm, now just okay. Base register addressing mode. This is somewhat similar to, if you recall, then within operating system, we have done these kind of calculations for converting relative address to absolute address, right? So what does it mean? There will be a base register address value that needs to be added, and then only we will be going, or we will be getting the address of the final operand. Okay. Now recall the scenarios that we have seen with respect to various perspective of the addressing mode, and security was one of these. Right. So ultimately, I should be having merely if I am having the address that will not do the thing. Ultimately, I should be having the address, or I should be having the value of the base register as well. Then only I can reach to the final address, right? So this is usually done in some cases where supposedly I have written some program, and supposedly we started with the 0th location, and finally say it be concluding to 255 location somehow by having the various variable. So this is relative in nature. Okay. Now this is being brought, or this is being made available within the memory, and memory I found that okay, the 0th unit is mapped to the address 15549, right? So if that is the case, then for calculating the next address, I'll be adding up 1 to it. So 155 49 plus 1, that is 15550. 15550 will be the next address. So ultimately, for getting any of the address, because this is relative in nature, so I will not be able to reach anywhere. Or even if I reach it, say it be if I went to location 255 for getting this value. So I will not be getting this value because ultimately 255 may be holding some another value, but the target was to reach over here. For reaching over here, I need to have the value of this base register, right? And that is 15549. So once I add 15549 into this, finally I'll be getting the address to be referred. Okay. So operand address. So R1 is there, and accumulator is also there. Okay, so ultimately you should have the value of the base address over here. Okay, so base address, you may assume that this XR is the base address. Okay, so that way, operand, that is, if you are referring to 500, we need to add 100 into it because 100 is the base address. And finally, 500 plus 100, that is 600. So whatever the value is stored in 600 needs to be referred. Right? So here, don't get confused with the value of R1 because R1 is now a totally different entity. But right from the beginning, we are taking this example. That's why. But suppose the address that comes out is 500, adding 100 into it because 100 is the value of the base register because we are assuming that XR is our base register. And then this is how we have fetched 900. Next is relative
Sir, one question
addressing.
there. Sorry
Yeah,
to interrupt. One question there.
yeah, wait, Patrick.
Yeah, here XR is the base address. From where that 500 value is coming, I'm not clear on that. It is the index value, right, which we need to add to base address.
Yes.
Where it is stored, as in, I thought R1,
Mm,
that's kind of a typo wherein R1 contains the index and XR is the base address. So we need to add both of them and get the address. I'm
yeah,
not too sure
so
from where
that can
500
be
is given.
considered. No, no, you are also correct. The only thing is, uh, this is just to exhibit the case where R1 may not be the value to be referred. Say it be if I'm using some another variable and some value is being stored in that variable, just for that particular case, this difference is being created where rather than using 400, we are using some address that is being referred, which is 500 and adding 100 to it, right? But in ideal case, what you are saying is correct that if this for this particular example, rather than if 500 is not the value, and if we have to pick it from one that is 400, we will add into 100 into it. We will reach the 500 location. In that case, the value that will be fetched will be 800. Right. So the only intention to use 500 here is just to exhibit that, okay, if it is given that 500 is the value that is to be referred, irrespective of what is available in R1, if it is given that, okay, 500 is the relative address to be referred, then what exactly will be the value that will be fetched?
I think,
You
sir,
can consider it
it's
that way.
their address is given in the image 500. That's why they are considering in 201 address.
Yeah, so ultimately, what happens is you will be having the program counter, right? And through program counter, you will be knowing that what exactly is the next address, next instruction to be executed. Okay, so that is one way. What you are saying, that's what I'm saying, that whatever is referred, so you have to pick it. Usually the numerical that are being referred. So supposedly, if this address is not being given, right, and I haven't given this 500 as well, and the problem states that, okay, the addressing mode needs to be referred is the base address on this particular base address or the base register addressing mode. Okay, so if that is the case, right? So if this is the case, then ultimately you need to take the R1 Okay, and within R1, the thing is ultimately you should be knowing that whether the value that is stored in R1 will be a value or whether it will be a address. That all will come through the addressing modes, right? So that way you have to find it out as exactly from where you have to find the final value of the variable. Got it?
Not still, sir. Can you come on the earlier slide, sir?
Yeah.
So here what I felt is, see, we have a base register which is going to hold the base address, and
Yeah.
E seems to be the index which we need to add into the value present in base register to ultimately get the exact memory location from where we need to pick up the operand, right?
Yes.
So base register is the one who is going to hold the address, and E is going to hold the index. For example, if we consider array case, for example, it contains 100 locations, for example. So my
Yes.
thought would be base register would contain address of 0th element, and A would contain a value, let's say 15. So I add that 15th index into base register's value. That will eventually give me 15th location of that array
Correct.
address of, and then that operand will be picked up that way. I I'm not clear on how that translated to the example which you're trying to show.
So whatever be the base register value that we need to add up to the final relative. That's why this example was given, that relative addressing.
So it is an index, it is not an address, right? Whatever A holds is an index. It is not actually an address. Is that understanding fair?
So what you are saying is whatever be the base register's value, but index addressing is somewhat different. How can I name you? Ved Pathak, right?
Yuvraj.
Yuvraj. Okay, sorry, but it is being written. Yeah. So Yuvraj, index addressing is totally different than what you are seeing over here.
Okay.
Uh, we'll see that index addressing. I think the problem here is the diagram that is creating the confusion. But
Mm-hmm.
just go to the logical thing that base ad register addressing mode. So you can say that it is a predefined register called the base register to hold the base address, and the
Right.
instruction itself specifies an offset
Okay.
relative to that base address, right? So,
Right. Offset is value, as in if we consider an array example, then from 0th location, how what is the offset
so
which
that
I need to make
offset
use of?
is my
Hmm.
relative value. So say it be
Okay.
if the
Hmm.
example
Hmm.
that we have taken from 0 to 255 we are moving. So
Hmm.
this is ultimately the offset that we
Exactly.
will be taking.
Exactly.
Yeah.
So I'm calling it out as index incorrectly, but it is an
Yes,
offset.
yes.
So it is a
Correct.
plain number. It is not a
It is
memory
a plain
location,
number.
valid
It's not
memory
a.
location. Hmm.
Yes.
Okay.
So that is merely a relative addressing, or you can say offset, that needs to be added into the base register.
Right. I see.
Yeah. Okay.
Sir, that this addressing, which way the address will be resolved, I think, is it I mean, directed by the op code, I mean, instruction, right?
Yeah, obviously.
Okay, yeah.
Not only
That will
opcode,
define
but
it is base addressing or it will be direct addressing.
opcode and ultimately the ISA or
Ah,
your
okay.
instruction set,
Mm-hmm. Yeah.
right? So suppose you are writing the hypervisor and there you need to refer to particular instruction, and finally how exactly the addressing modes are to be utilized. So that way you need to refer to the instruction set as corresponding to a specific opcode where exactly you will be getting the final value.
Yeah. So
Yeah.
because suppose here I am doing add, now this can be two-way. Direct value also can be there, or address also can be specified in the operands, or a
Yeah.
base addressing. So that specific machines bytecode or this opcode specify, right, how the address will be resolved.
Mm, can you come again?
I mean, it's machine to processor. This opcode will vary, right? That will how it will resolve the parameters or the operands. That as you mentioned, it
No,
depends,
no,
right, on the
opcode
hardware.
will not vary processor to processor. If you are using same instruction set architecture,
Okay.
ultimately opcode will remain same. If you compare 32-bit with that of 64-bit, definitely the length and the opcode may change. But if you are talking about 64-bit architecture, then in all the cases, opcode will remain same.
Okay.
I'm telling about the machine level opcode, right? So there will not be any change in opcode.
Okay, then question would be something like, sir, if I want to kind of provide direct value inside the instruction, let's say hash
Hmm.
10 is something which I want to add to register R1, and second
Hmm.
example which we saw, add
So hash
R1,
10 is just
uh,
an example
a
where the
constant
user,
value.
yeah,
Hmm,
constant value, correct, huh?
correct, correct.
Huh.
When I need to specify something like add R1 and R2 and keep the value into R1, for example.
Yeah, yeah.
So when we instruction ultimately is add, so opcode is going to remain same for both the instructions. How would the underlying mechanism know that I need to use the value specified directly in the instructions, or I need to go to register R2 in order to fetch the value?
Okay. So you are asking that ultimately if we are keeping the instruction as same
Hmm.
and different addressing modes are being
Hmm.
utilized. Okay, even I need to check this particular thing, that how exactly the difference will be made. Because
Correct.
ultimately we need to get into the machine level language,
Hmm.
right? So even this question was clicking to my mind that how when I was going through that how exactly when we will be having same instruction, but it may be having different values. Say it be if it is having register or say it be if it is having indirect mode.
Correct. Correct. Hmm.
Yeah.
Either
So
ways,
I'll
when
go
opcode
through
remains
it.
same. Hmm. Okay.
Yeah. Because we need to deep dive into the machine learning concept for this, as how exactly that differentiation will be made. But primary phase, yeah, I think that ultimately the machine instruction will altogether differentiate it. But again, if instruction remains same and only we are varying the operands in
Hmm.
terms of the register, and then we need to check. I'll just go through it and we'll discuss it in the next session, right?
Sure. Sure. Gautam, was
Yeah.
that close to what you were trying to ask?
I got answer what sir mentioned earlier. Yeah, I got it.
Okay.
Yeah. Right. So relative addressing. So base address. Next is the relative addressing. Again, what Yuvraj was saying with a different tweak. So you can just have a look. But this time it will be coming from the program counter. You can just have a look that we are having the opcode. Better we'll understand this with the example. So program counter is having a value 202. That is after reading at instruction 200. Okay, so the program counter has the value 202. So the operand address here comes out to be 500 plus 202. Again, the same thing, but with a different, what I can say, hardware configuration where whatever be the address that we need to refer. So within that address, we will be adding the value of the PC, that is the program counter. So that is 202, that is 702. From 702, we'll be picking it up. That is 325 will be the value that will be fetched. So this is our relative addressing mode, where now I am not saying that some value will be registered or stored in the base register. So even if XR is there, 100 is there, but if the addressing mode is relative addressing mode, in that case, we need to come up with addition of the program counter within the value or the address that is to be referred. Okay, so 325 is the value.
Okay, sir,
Uh,
is there a typo program counter value is being shown as 200 there and we're considering it as 202 or
uh,
relative after reading instruction at 200?
yeah,
Initial
yeah.
value is
So here,
200
yeah,
and
this
then
is type.
I was talking about the value inside the box right at the top. PC is 200 and then we are using value as 202 after reading the instruction at 200. Shouldn't it be
So
201?
PC will no 201. We are having the address to be referred. So that's
Okay,
why.
okay,
So it is already being processed. So this is the initial state.
okay,
Yeah. So once we will be moving, so the next value that will be stored will be 202.
okay.
Yeah.
And we are making use of the new value.
New value.
Okay,
Mm. So that way it will be your relative addressing mode indexed. So this is something that you was saying that index register. So specifically within the instruction set, you will be having some register known as index register. The overall concept will remain same as that of base register, but now rather than base register, you will be picking up the value to be added into the offset, or you can say the relative address will be your index register, or the value of index register will be added to it. Okay. Again, uh, this is the assumption that will come out. Say it be if I am saying that XR is considered to be the index register, then the address to be referred is 500. I am adding the value of the index register, and the process ultimately remains same, that we will be fetching the value 900. The difference, I hope you got the difference. The only difference is earlier we were referring it as base register, okay, and in some instruction set you may be calling it as index register. So it's not only the difference in name. The thing is, I'll tweak this, that rather than XR, we will introduce some another register. But right from the beginning, we are taking this example. That's why it is being utilized here again. Okay. But the overall concept is different, because when you see the architecture, when you deep dive into computer architecture, so there you will be finding that different types of registers are there. And index register is one such register. So therefore, the overall concept is different, where base register may be any general purpose register, where value is being stored, while index registers are the specialized registers where whenever we need to store the indexes, so at that time it is being utilized through the instruction set. Okay, so if you see the mathematical perspective, they may seem similar to you, but think it from the fetching logic, that ultimately whenever I need to fetch the value, okay, so at that time ultimately I should know that which particular addressing mode it is following. So whether it is index register, if it is an index addressing mode, then I need to refer the index addressing mode. Sorry for the bad throat. Okay. Otherwise, if it is a base register, again I'll find it out as how exactly this addressing is being referred, right? So what the question that is being pointed out by you, Raj. Okay. Auto increment, auto decrement, quite
Sir, one question on
clear.
earlier slide.
Yeah.
Here, can we assume that index register will be accessed more often as against the general purpose register?
Yeah,
Because
obviously means
because hmm,
whenever we need to locate it, so the reference will always be fast when it comes to index register, just like we use in databases, right? So whenever we use indexes in databases, somewhere the overall query processing get faster, right? This is the question that you are asking.
no, no, I'm trying to ask in another way. Let's say base register holds the base address of array, zeroth location of array, and index
Yes.
contains just 1 to 4 value, right? Which is the
Okay.
offset of the value which we need to eventually access using the address computation mechanism. So index register will be the one which will be accessed more, as in we need to increment that index every time, right? Base register value is going to remain constant because it is zeroth location's address, while index is the one which is going to be incremented every time we perform the operation on the array, right?
Yeah.
So
So yeah, correct, correct. So
index will
index
be
will be
accessed
referred
more,
more.
plus it will be manipulated more as against the base register. Is that the case? Is what I'm trying to ask.
But both will not be utilized simultaneously. No? Means why you are assuming that base register and index register will be utilized on a simultaneous node. Either you will be going for this particular addressing mode, that is base register addressing mode, or you will be going for index addressing mode.
Oh, I see. I see.
Yeah,
Okay.
yeah.
Okay.
Got it?
Mhm,
Yeah.
mhm. Okay.
Means I think this has created the confusion, but it is either or. Either you will be going for index or you will be going for base, right?
Right. So index
Mm.
register will hold the address which we need to
Yeah, yeah.
add up
Add
in
up. Yeah.
index addressing. Okay.
Yes, yes. Yeah. Okay. Auto increment, auto decrement, quite clear. Means whatever the value is stored, apparently you have to increment it, decrement it, and store it there only, right? Right. So again, the problem statement is not clear over here, but ultimately here what they have done is they have picked it the value from the register and referred to this particular value 700 and decrements before reading, right? So that way it is 399 and the value that is fetched is 450. Okay. Uh, or it can be in the value if it is coming to be uh, the direct mode. So here it is indirect mode where the address is being stored, and because of that the address is being decremented, and finally the value stored in that particular address is being fetched. So this is somewhat equivalent to that ampersand operator that we usually use in C, C++. Okay.
Sir, sorry,
Just
that
go through a
wasn't
few
clear.
of the questions. Yeah,
That
Yuvraj.
wasn't clear to me. When we say auto increment, do we mean address being manipulated or the value at address being manipulated?
No, no, that is value at address being manipulated. But here the example that is being taken is that's what I am saying. The problem statement is not clear over here, but what you have pointed it out is correct. Ultimately, it should be the value.
Hmm.
But if you recall, supposedly if I'm writing a code where say it be if I'm having int, use some normal. Yeah. So suppose I'm writing int star p. Apart from that, there is one more variable a and int a equals to 10, right? So after that, I'm writing p equals to ampersand a, right? Uh,
Yeah.
है ना? And within this, I will be having, say it be rather than this, I am taking an array int a of 10, right? And p equals to ampersand a of 0, okay? And if after this, I'll be writing p plus plus. So ultimately, here the address will be incremented.
That's correct.
Yeah.
Yeah. Okay, so the example which you showed was in that particular regards.
Yeah, so it is with this particular context. So that's why I'm saying the problem here is not clear what
Hmm.
exactly means, whether it is the value to be incremented or whether it is the address to be
That has to be
incremented like
included.
this. Yeah.
Okay.
But in a definition, sir, it's mentioned register need to be incremented. Go back to the slides, one previous slides.
Okay, that you are saying it in problem, this one.
Yeah, in a
Just a minute. Yeah.
definition of the increment and decrement, auto decrement, increment.
This one?
One more, one more slide back. Here, they are saying that this is the similar to the register in indirect mode, except that register is incremented after register value is accessed.
That I got your point. But the thing is, you cannot explicitly say that it will always be the register or it will always be the register that will be incremented or decremented. In case of auto increment, what will happen if you perform some auto increment operation on some operand? Say it
No,
be
but
if
here, sir, sorry, but here we are talking about the addressing mode. So that should be the address only. Why the value?
mm, say it be simply if I'm writing say it be if int j is there, right, and I have written j equal to 10, if I'm writing j plus plus.
Yeah, this is like it's a value increment because we are talking here in terms of value, but here
Yeah, but ultimately, don't you think that if I am writing j plus plus, right, so somehow down the line, ultimately the value is being incremented. First of all, I need to fetch the value. After fetching the value, I need to increment it
increment the value.
and yeah, increment the value and again store it back to j.
Yes, but here we are not increasing the address. We are just increasing the value and addressing in the same variable,
Yeah, so down the
same address.
line again, we need to check the machine learning instruction that is going. Sorry, not machine learning, that is machine instruction.
Okay.
Got the point? There is a bit of confusion. What I'll do is I'll think or I'll correlate it with the perspective of machine language so that whatever be the questions as raised by Yuvraj, and you also have pointed it out correctly, but ultimately many times we have to go with incrementing the value as well. So if instruction just like this is there, ultimately, this is, you can say it is not high level language, but you can say mid level complexity language. Down the line, it will ultimately be converted to machine level language,
Mm-hmm.
right? And then finally, the addressing modes will be referred. Definitely, here we are doing some kind of abstraction, but we need to check that how exactly it is being converted to machine level, and then we will be able to find it out as how exactly this will be considered. So what your point is that ultimately because it is addressing mode, definitely the auto increment and decrement will be happening corresponding to address. But the whole quest that we are getting right from the beginning is ultimately to get the value. Okay.
Mm-hmm.
So if uh, ever we have any auto increment or auto decrement corresponding to the value stored, means I need to check whether there is some machine level instruction where we can issue, or some machine level instruction where auto increment and auto decrement is there or not. So for that we need to go through the instruction set architecture of 64-bit CISC or whatever be the Intel 64-bit architecture document we need to refer. Okay, and then we will be able to find it out exactly. So if there is any instruction where we can increase the value stored by having those auto increment or auto decrement, then this point will be correct. If not, and ultimately only the auto increment or auto decrement would be possible only in addresses whenever the addressing modes are being referred. So in that case, this will not be the thing. But we need to check that whether there is some machine level instruction that corresponds to auto increment or auto decrement. I hope
Yeah.
this is clear, but I need to refer that document in this case. Okay, I'll refer it.
Okay.
I have already downloaded it, but it's a long document. Means I tried to go through it because I was taking this subject. So I have downloaded the instruction set of Intel, but it's a long document. So, but because input is coming from your side, so that's why, means I'm sure now I'll be going through that document and we'll be discussing it in the next session as well. Okay.
Okay, sir.
So this was corresponding to the addressing modes that will be utilized. We will see that how exactly will be the difference between RISC and CISC as compared to reduced instruction set and the CISC. What exactly is the difference in case of addressing modes? Okay, but before that, we will see that what exactly is hardwired and microprogrammed control unit. So control unit, you all know that is an integral part of von Neumann model and one of the major component of von Neumann model. Okay, and comes in two variants. One is hardwired and other one is microprogrammed. So just go to the verbal meaning where hardwired control unit is you can say that it is circuit based, and a complete hardware infrastructure will be available that is driving the control unit, or through that particular hardwired, or that hardware specifically, the control signals will be generated. While in case of microprogrammed, definitely down the line there will be some hardware on which this microprogram will be written. Okay, but again, the thing is, the control signals will be generated based on the microprogram or the program written on the base hardware, right? So I'm not from the core electronics background, but the thing is, here we will be continuously growing from the hardware side, and you can assume that if I'm doing each and every control signal or generating each and every control signal through the hardware configuration, say it be the combination of chips and all that. While in case of microprogram, definitely there will be some storage or some IC where this microprogram will be there, responsible for generating the control signals. But definitely now, with the basic nomenclature or the verbal meaning, you would be able to point it out, the core differences between the hardwired control unit and microprogram control unit. So this is usually fixed set of logical gates and circuits, because it's totally done by hardware. Again, you can have an analogy of your say it be direct addressing, and your the other one that we have seen in terms of cache, right? So we have seen direct, and associative was there, and somehow we have seen the set associative. Okay, so here everything will be governed by the hardware side. Okay, the control signal for each instructions are hardwired into the control unit. So corresponding to any signal to be generated, ultimately it is coming out through the hardware. And definitely, if everything is being controlled through hardware, it will be simple and fast. But I think you have already predicted it, that it would be inflexible. Okay, suppose I have to make some changes into it, then it will not be that easy to make the change, because everything is coming through hardware, and appropriate circuitry is already being established for the generation of the control signals, right? So in case if any changes are to be done, right? So those changes will be somewhat difficult in case of hardwired control unit, right? So it can be viewed as a state machine that changes the state from one to another. Uh, Again, because it is a control signals needs to be generated. Okay, and yeah, risk architecture. If you recall, in risk architecture, we have seen that risk architecture is based on hardwired control unit, because the instructions are quite simple. So that's why it's okay if they go with the hardwired control unit to generate the control signals. And that's why it is somewhat faster in nature, right? So this is a diagram that is being picked corresponding to hardwired control unit. So everything is being controlled through hardware. The overall or totally opposite to this is your microprogram control unit. So a microcode will be written to execute the instructions, ultimately to generate the control signals, right? So set of instructions can be modified or updated So the advantage that we are having with microprogram control unit is somewhat easy whenever some changes are to be done with reference to the control signals to be generated for a specific architecture. So only that microprogram needs to be, again, think it from the perspective of the manufacturers, because as an end user we don't have anything to be done over here, right? Because neither we are analyzing the hardwired control signals, or nor we are analyzing the microprogram control signals. The thing is, think it from the perspective of the manufacturer. When say it be if at a later stage they have to make some changes within the control signals, because ultimately that is part of your uh, what I can say, organization, right? And not because what are the control signals that are being generated will be part of your computer organization, right? So that way, the manufacturer have to make the changes within the control unit in case it is hardwired. While in case of microprogram, the same hardware can be utilized, and ultimately they only need to change the set of instructions that are being written, or the microcode that is being written to the microprogram control unit, right? So stored in memory rather than being hardwired into the control unit. Okay, slower because hardware, we are not achieving it through the hardware circuitry. Ultimately, a low level code is being what I can say, the low level code is responsible for generating the control signals, and that's why it is slower in nature, but with an advantage that the same hardware will be utilized in order to change any of the control signal that will be there, right? So flexible and easier to modify, uh, obviously, and so you can see that ultimately programmers will be utilizing it. Okay, so this is your microprogrammed control unit. Can go through the differences as what exactly are the differences among the two. Next is how in terms of cloud infrastructure, but because we have already associated it with the respective architecture, right? So I think the difference is quite clear to you that because microprogrammed, you are having CISC based, and in RISC, you are utilizing the hardwired control unit, right? So wherever means if you have adapted risk, or just like in Graviton, AWS Graviton, they have adapted risk. So explicit or implicitly, the hardware or that particular hardwired control unit will be utilized if risk architecture is being used. Rest, these are all the advantages, say it be speed and efficiency, complexity and flexibility that we have already discussed, right? So, where exactly the control unit is present if we talk about the cloud infrastructure? So, control unit will be there in server CPUs, right? Not only this, control unit will be there in networking devices. So, whichever be the networking devices, the switches, routers, gateways that are being usually utilized. So the managed switches, the routers, the gateways, they are usually having the control units. And definitely, if we talk about NAS and SAN, that is network attached storage and storage area network, which is totally an isolated managed network, right? So, sorry, I see network, it is storage. So that there also you will be utilizing or using this control unit. right? So again, the same case, ultimately you need to think about the legacy perspective, that if you are utilizing CISC-based machines, so that way ultimately it will be the microprogram control unit that the manufacturers have to go. But with reference to different implementation, the advantages may be identified. Say it be in server CPU, if we go with the hardwired control units or the RISC-based machines, obviously, whatever be the advantages with the RISC-based machines will automatically be applicable over here. But just to give you a perspective that okay, it's not only the CPU where the control units are being utilized. There are other devices as well where they are utilized. So that way, these slides are included. So you can just have a look. So in storage, whatever be the advantages of hardwired will automatically be applicable over here. Okay. So now coming to the pipeline processor. Uh, if you have heard, so today we'll lay down the foundation as what exactly is the basic analogy with reference to pipelining, and then we'll deep dive as how Intel and these manufacturers are utilizing the pipelining within the hardware itself. It's not like that. Uh, Over and above, you have to define the layer of abstraction for getting that pipelining achieved. Ultimately, processor itself are having the overall concept of pipelining, right? So this is an example of serial execution. Say it be if different tasks are there. So if you see this particular image, then you can consider it as a four loads of dirty laundry that needs to be washed. So the four loads are A, B, C, and D, right? And not only washed, they need to be dried and folded. So four loads are there, and three different operations are there. So first operation is washing, second operation is drying, and third is folding, right? Okay, so just have a look at the diagram. So we can put the first load for 30 minutes, dry it for 40 minutes, and then we can fold it. That again took 20 minutes, right? So this is 30. You can see that this yellow one, you consider it as washing. This is drying, and this is folding. So altogether, 70 and 90 minutes are being required for one load. So it is starting at 6 p.m. and somewhat completing 30, 40, 20, 60 at midnight, right? Almost taking 6 hours. Okay. But what if we can do some task in parallel? Okay. So say it be we can have a smarter approach to this particular problem where we'll be putting the second load of dirty laundry into the washer after the first was already clean, right? So when the first load was clean, definitely don't take it from the perspective of automatic machine where your dryer and washer comes with the same tub. Consider it as a semi-automatic machine when we are going through the analogy, right? So have the analogy in that perspective, where assume that it is possible that the hardware is supporting us, where when we are doing the washing or when we are doing the drying corresponding to the load A, at that time we can start the washing of B. And this way, just see that it started at 6 and completed at 9:20. We need to check 80, 1, 2, 3, 4, 180 and 210. Right. So all together, that is your 3 hours 30 minutes. Right. So it will complete at 9:30. Right. So something that was completing at midnight, because we are having the pipelining support from the hardware where we can have some task in parallel. So that's why we are getting the advantage. Same concept is being utilized in the processors. So we will see further how exactly we can have this pipelining. So if you recall, then again, these things are related with Murray's law. Okay, so in Murray's law, we try to increase the speed and remaining where the cost is again remain constant, but try to develop the speed in every 2 years by having more number of processors within the same density, right? So that way we will be having the concept of pipelining as an alternative where in Murray's law, after a certain level, we were not being able to achieve the exact performance per watt. And that's why apart from the multi-core, so these are all the solutions that comes out for having the parallelism that pipelining multiple execution units can be identified and at the same time multiple cores, right? So these are all the solutions for having a better system performance. So if we think it from the processor perspective, so you can see that I may be having 4 instructions. So corresponding to those 4 instructions, if there is no dependency among these 4 instructions, I am having a clock and say it be if I can start one instruction fetch over here. At the same time, when this instruction is being decoded, at the same time, if my hardware supports that some another instructions fetching can be done in parallel with the decoding of this, right? So if that is at all possible, then definitely we can have the concept similar to that of pipelining, right? So we'll see how exactly this is being carried out in Intel architecture, because the document that I have referred for this is the Intel architecture. Okay, so that's all for today. Any questions? But it's really good means today few of you have interacted, so that way I'll be somehow reading that architecture document in much of the depth, right? So thanks to Yuvraj and Ajit. And I think one more was there. I think Gautam was there. Yeah.
Yeah, sir, midterm, how much module will be?
Till today.
Okay, okay. Thank you, sir.
Yeah. Okay. And still I'll brief you in the next session as how exactly will be the pattern in terms of the moderate complexity, or you can say analytical questions. So
Sir, another question. I mean, in second half, I mean, after midterm, are we going to see, I mean, some practical infrastructure management, cloud infra?
yeah, yeah. So what we are having is we will be having some virtualization and
Mhm.
containerization concept.
Okay.
So this is somewhat theoretical, the first half. I'll quickly sum up the fourth and fifth module, where we have to go through processes and all that. It will be very interesting from data centers. We are
Mm-hmm.
having modules for data centers, then virtualization. Within virtualization, we'll be having some practical aspect with reference to VMware workstation and all. Then Docker containerization is there, so
Yeah,
we'll be
because
having some experience.
those handy
No,
things
no,
will
rest
come
assured
in.
means we will be having a lot
Yeah.
of practical things. At
Okay,
last, we
sir.
will be having OpenStack. So we will be having installation of OpenStack not only on a single system, but because we have done it on one of the cluster that we are having at our premises. So that way I'll be connecting it through that particular location, and apparently will make you aware of the overall deployment of OpenStack to cluster hardware, right?
Okay, okay, fine then.
Yeah.
Thank you,
Okay.
sir.
Yeah.
So, sir, next section will be revision only, right? Only revision.
Yeah. Manish, can you come again?
Next section will be just revision for the
No, no, no.
midterm.
Next session will not be revision. We will be continuing. Just only for your ease, I am dropping out the next session from the
Okay.
mid-sem. Yeah, yeah.
Okay. Okay.
Yeah.
Thanks.
Okay.
Can
Anything
you please
else?
upload this? Can you please upload this PPT, sir?
Yeah, yeah. It's already there. I think the third
No,
one.
it's not there actually.
It's not there.
No.
Okay. Okay. Okay, I'll upload it. There are some corrections that we have identified today, so I'll do the corrections and then we'll upload it. Okay.
Okay, sir.
Okay. Okay. Thank you. It's a good interactive session today, and I hope that subsequently we'll be having similar sessions, because ultimately that puts pressure on me as well to deep dive into it, and I like that particular approach, right? So be interactive. Yeah. Okay. Thank you. I'm
Sure.
ending up the session.
Thank you. Thank you, sir.
Sir,
Bye.